Now here in this question it is asked that let Np and Ne be the number of holes and conduction electrons in an intrinsic semiconductor. That is, Np is the number of holes and Ne is the number of conduction electrons, that is free electrons, in an intrinsic semiconductor. So therefore, for an intrinsic semiconductor, which of the following options are correct? Whether option A, number of holes greater than number of conduction electrons, option B, number of holes is equal to number of conduction electrons, option C, number of holes less than number of conduction electrons, and option D, number of holes not equal to number of conduction electrons. So out of this option, which option is correct for intrinsic semiconductor? Now let's start with the basics here. Semiconductors basically are divided into two types. One is intrinsic and extrinsic. Intrinsic semiconductors, as we know, are the purest form of semiconductors without any impurities or doping done. Extrinsic semiconductors are prepared by adding a sufficient amount of impurity. Now our question is based on intrinsic semiconductor, and let's take an example of a silicon atom as an intrinsic semiconductor. So here we can see there is a silicon atom shown here. This is the silicon atom shown, and in this atom we can see that there are 4 valence electrons, that is electrons in the outermost orbit are 4. So here you can see this is 1, this is 2, this is 3, and this is 4. These are 4 valence electrons. Now when we have many silicon atoms together, so when they are combined, there is a formation of covalent bonds where the valence electrons of one silicon atom will get combined with a valence electron of another silicon atom, and that bonding is called as covalent bond. So here if we concentrate on a silicon crystal lattice, you can see that we can have a covalent bond here between two valence electrons. Here we can have a covalent bond, here we can have a covalent bond. So it is between the valence electron of one silicon atom and valence electron of other adjacent silicon atom. So here also you can see a covalent bond, here also you can see a covalent bond. Now at normal or temperature, a few electrons which are forming this covalent bonds can break the covalent bond and become free electron, as shown in this figure here. So here you can see at normal or temperature, in case of the silicon crystal lattice, we can see that a few electrons, the electrons which are forming the covalent bonds, a few electrons break their covalent bond at normal temperature and become free electrons, as shown in this figure. Now in this figure you can see that we are having a electron which was here in this place has come out and become free electron. So here you can see a free electron, and the place from where it has come, that is assumed as a hole. Now this is assumed as a hole. Now even here you can see the electron which has come out has become a free electron here, and this is assumed as a hole. This is assumed as a hole. Even here you can see this has become a free electron, and this is assumed as a hole. This is the free electron, and this is assumed as a hole. Even here you can see the electron which has come out at normal temperature, which has broken the covalent bond, and it has become a free electron here, and this is assumed as a hole. Okay, now whenever the electron which was forming the covalent bond with the adjacent silicon atom valence electron at normal temperature, it has broken the covalent bond and it's come out. So whenever the electron comes out and becomes a free electron, there is a hole created at the place where it was originally there. Okay, that means whenever there is a free electron created, there is a creation of hole also. Now if you see the energy band or diagram here in this figure, so when we say about energy band or diagram here, so here you can see initially when the covalent bonds were there, all the electrons were in the valence band. So this is the valence band, all the electrons were in the valence band. But at normal temperature, we saw that few electrons broke away and broke the covalent bond and became free electrons. So those free electrons, they shifted to the conduction band. As they become free electron, as they become the conducting electrons, they came to the conduction band, and the place from where they had come, that were assumed as hole, and the hole are now situated in the valence band. So you can see in this energy band diagram. But as a whole, we can just conclude that whenever the covalent bonds are broken and whenever one of the electron comes out and becomes free electron, there is a hole created in its original place. That means the absence of electron in the bond is assumed as a hole. That means whenever there is a free electron, there is a hole created also. Whenever there are free electrons arising, that many holes also will be there. That means number of free electrons, number of conducting electrons will be equal to number of holes in an intrinsic semiconductor. So in an intrinsic semiconductor, number of holes will be equal to number of free electrons. So here you can see intrinsic or undoped semiconductor have free electrons and holes. Both of them are generated in pairs because they are thermally generated and are equal in numbers. So because of this, the second option, that is NP is equal to NE, is the correct option. That is number of holes is equal to number of conduction electrons or free electrons in an intrinsic semiconductor. So option B is the right answer.